basically.
I've got it. Got it? Yep.
Yeah. I need your. Take care.
Yeah, it's okay. Please, I mean, so we have Professor Hiskens from the electrical department today. He's the Vennema Professor of Engineering from the Engineering School, and he has a course with the same title, and he's here to give a more, I would say, non-technical flavor of what are the challenges associated with integrating renewable energy into the grid.
Okay, great, thank you. Thank you for the invitation to come and talk to the group for coming along. Warmer in here, certainly outside, so I guess they have something to work. Okay, so the talk kind of gathers together a number of ideas and at a fairly kind of introductory, kind of high-level view. So there will probably be lots of, in your mind there may be lots of questions, so feel free to ask those questions as we go along. So just as some background, my research group has been doing various different projects associated with integrating renewable generation into the grid. My background is a grid person, so doing power systems is what I've done for a long time. And then one of the exciting new things that is happening with power systems is dealing with the issues that arise from renewables. The other exciting thing is the opportunity to control loads, and I'll mention very briefly at the end how these two things can come together. As a starting point, so, okay, that didn't show up very well. It looks great on my screen. This actually shows a composite photograph that was put together by NASA, and it highlights where the light patterns are around the world, and that correlates perfectly with where you find the kind of development, first world countries, and so forth. So it's sort of showing up a little bit better. There's enormous amount of light across the United States, particularly in the eastern half, and I'll show you a diagram later which identifies where the transmission lines are in the US, and we'll find major correlation over the eastern half of the US. When one moves to looking at Europe, again, you can find see where the development is. If you look around the Mediterranean, it's ringed by this light. If you look down to Australia, you can find Brisbane, Sydney and Melbourne, and not a whole lot else because there's wide open spaces, and the electricity usage is very much driven by population base. So this illustrates kind of like where you find development, it's building on a reliable and cheap, economic and reliable source of electricity. It's fundamental to all forms of development. Okay, so that's just some motivation that, at least for me, that what I work on has some impact on the world. Okay, so another view, so that's the very high level view, and then one can start to think about, okay, well, what is a power system? I have two slides that are complementary in a sense, that break out the various different aspects of the power system, because I'm not sure how many people have ever actually really thought about what makes the process of producing electricity and getting it to the outlet. So in the traditional form of electricity supply, there are major power plants that produce bulk electricity, typically in the hundreds to thousands of megawatts type capacity. And they then transmit or transport that electricity across the transmission line, which is a high voltage network. It's high voltage because the higher the voltage, the smaller the current. The smaller the current, the smaller the losses in the network. But high voltage, sort of like the freeway system of electricity, and you can't deliver high voltage to individual users, so there needs to be a process of reducing that voltage down through a substation to a sub-transmission level. It's still up in the 120 to 40 kV type range. It then gets transformed down to the 13 kV to 4 kV type range, which is the lines that you see out around the residential area. And then we're probably all familiar with seeing these pole top transformers that are connected to the customers at the end. So all of that makes up electricity supply, and it all has to work together, otherwise one will either be creating overloads which need to be dealt with, or be underutilizing plant, and that's expensive. So there's a lot of design that goes into making these things all work together. When wind comes along, for example, and I'll probably focus more on wind integration because that is a bigger player in the renewable energy world in the US, at least at the moment. So when wind comes along, there are different philosophies for different localities of where they put the wind. If you're over on the west coast in Portland, there's an enormous amount of wind, and that's being put into the transmission network. So it's connected in at the transmission level because you're talking thousands of megawatts of wind capability, so you need the higher voltages to be able to carry that large amount. When you move to Michigan, there's a lot of work going on in terms of putting wind into the thumb area, and that wind will go in at the 40, or a lot of it will go in at the 40 kV level. That's the existing infrastructure, so it's using that existing infrastructure. It's actually too much wind for that existing infrastructure, and so it will create all sorts of voltage control problems, which make for a really interesting and rich research field. And we're working with Detroit Edison and addressing some of those issues, but the point is that wind is going in at 40 kV because of economic reasons. Here, it's going in at 500 kV in Portland, in Oregon, near Portland, again, for the economic reasons in that case. So there's no sort of one notion of interconnection that fits all. The other view of the complementary view, it's all the same thing, it's just expressed in a different way, but it sort of highlights the various different voltage levels, and if you're looking out across a power system, which probably no one's ever thought of doing, when you see the towers, that implies higher voltage. When you see smaller towers or poles with intermediate size, that's the sub-transmission, and then you're familiar with the distribution system out around the residences. Any questions? So that's sort of like what you anticipate the various different pieces of the power system. Yeah.
I got caught blindsided on vacation once by very high voltage DC transmission. What's the story right there?
So if you're transmitting a lot of electrical energy point to point over a long distance, then DC becomes a cheaper option because it only has 2 wires instead of 3 wires. it actually turns out that the resistance is lower in DC than it is in AC as well. Not too much around in the US, so there are a few DC installations in the US. Probably the most significant is what's called Pacific HVDC intertie from Oregon down to Los Angeles. It's a plus and minus 500 kV or something. So there's an economic trade-off. What they do to produce DC is AC is rectified to become DC, transmitted over long distance, and then converted back to AC using power electronics at both ends.
Okay, it's not done mechanically.
It's not done mechanically, it's done with power electronics.
Did you say that was less common? Sorry.
So,
Did you say that was a less common method of electricity transportation?
yeah, it is. It's, you know, of all the transmission across the US, there's probably 5 or 6 DC in the thousands that exist in the US. Because it's a really sort of a niche market. It only becomes economic when you're carrying a lot of power a long distance. There's a new technology that has come available in recent years, and it's starting to find more applications. The other place where you do find DC is where it has to go underground, because AC at high voltage, for various technical reasons, doesn't work underground. So if you have undersea cables, then for a relatively long distance, then they'll probably be DC. So there's been a new DC cable installed underneath the San Francisco Bay to get electricity into the San Francisco Peninsula, because there just wasn't any capacity, any spare space to put new traditional power lines in there. In Europe, there's a lot of DC underneath the Baltic Sea in particular. So a lot of hydro in the Scandinavian countries, and then that needs, want to get that hydro power, cheap hydro power into the European market, and the only way to do that is to go under the Baltic Sea. The only way to do long undersea cables is DC, so they kind of lead the market in that respect.
I have a question on your thumb problem. There aren't any 345 kilovolt lines running up into the thumb?
There will be soon. There's not at the moment.
And that's the only reason you're not using them right now.
It's an interesting strategy that the wind will be quite distributed across the thumb area, and so to put new lines that would capture all of that wind generation would be very expensive. So the idea is to use the existing 40 kV, kind of upload it to the 120 kV that's through there, and then there will be this new 340 that will transport it down to Detroit.
And it's not far from there to Detroit anyway. So.
Yeah, but they will be reinforced by ITC in the next year or two, or whenever they get approval. Okay, so this is the transmission capacity, transmission lines across the US. And as I mentioned earlier, when you look at that photograph that shows where the light patterns are, it's predominantly kind of east of the Mississippi. And likewise, when you look at the transmission, that's where you find a whole lot of transmission capacity. In the west, there's large lines bringing cheap hydro down to California, where there's a sizable market, and then there's actually lines across. There's coal over here, so there's a good deal of transmission from the coal resources as well. California prides itself on how little coal generation they have in the state, but they buy in a whole lot from the neighbouring states. So I'm not sure they're really doing that much for the environment. Another interesting correlation is when you look at where the wind resources are in the US. So the colour scheme is these bluer, red, mauve kind of colours are better wind resources. So you find the best wind resources out in the Dakotas, put down through at the Texas Panhandle on the land. So if you look back at the previous one, you don't actually find very much transmission through there. So there's this dilemma of how do we exploit those wind resources? How much is it worth building a whole lot of new transmission to bring that wind to market? Interesting economic balance that has to be done there. Because nobody wants transmission lines in their backyard. In fact, nobody wants wind turbines in their backyard, but everyone wants renewable power. So there's kind of an interesting dilemma. The other thing that you do observe on this diagram is offshore wind capacity is down in the superb, outstanding and superb categories. Along the west coast and along the east coast and the Great Lakes. It's all very good wind resources. It's just that no one's worked out how to exploit it in the US yet. The drop-off, it's very deep on the west coast, so that makes it difficult there. The east coast is it's very feasible technically, but there's a lot of people there who don't want to look out across at the ocean and look at wind turbines. And maybe not surprisingly, the same with the Great Lakes. So the most useful wind resources are not exploitable for these aesthetic reasons. There's a scheme that Google was pushing at one stage, I've lost track of where it was at, to put the wind, to build wind generation sufficiently far offshore down through this region here that you can't really see it from the coastline. And then to build a DC, it's all underwater so it has to be DC, this big DC backbone through that area would connect up into the grid at the top and down at the bottom, and then there'd be a number of interconnections for DC. Very expensive. Interesting technical challenges, but very expensive. So that kind of establishes the wind patterns and the correlation of the wind patterns with population base as well. Any questions? Yeah.
Roughly, what's the number of all of these? If you were to harness all these potential areas of wind energy, how much power would they provide? Is that estimate in that?
I don't know the number. It's enormous. There's an enormous capability there, but it's expensive to do as well. There's a lot of energy. There's this open question on what happens if you pull the energy, a lot of energy out of the wind. How does that alter the climate? And various studies have shown that it will, and various studies have shown that it won't. And the truth is out there somewhere. But there's a lot of energy available. It's just in the wrong place and difficult to capture.
I have a question on what I think Detroit Edison calls utilization factor. How does that vary for wind power in these various areas? Does it change very much?
It does, and I actually have a slide on that later, but I'll talk about it now. Where you see these fair resources, and there's splatterings of fair resources, the thumb area is the best onshore for Michigan. It's lower quality wind, which means that it is more variable, and the wind speeds are lower as well. So out in the Dakotas, the wind is apparently always low. I don't know why anyone would live there, because it's cold and windy all the time. For an Australian, that just sounds miserable. But it apparently is strong winds and very consistent winds. And all the way down through the middle there. So the utilization factor is higher. It's still not anything like a centralized coal or nuclear plant. It's probably because of the diurnal patterns, but it's certainly better over in those areas than 20 to 40% is
In other areas?
yeah. Okay, so we've seen that figure before. I threw in this slide because people have probably heard the term smart grid around, and it sort of it means whatever you want it to mean, basically. It's more a sales pitch than a technical pitch. But in my concept of smart grid, it involves introducing feedback loops at the load end, and I'll come back to one form of that towards the end. But taking measurements through the advanced metering infrastructure that's been involved out, applying control to alter the load characteristics. That's at one end, and at the other end, at sort of higher voltage transmission end, tends to take on the form of what's called wide area control, where you're taking measurements from across this large, geographically large area, time synchronizing using GPS, and then building a control algorithm that's taking into account these wider measurements to implement various changes on the grid in real time. So you have sort of real-time control happening at the higher grid level and real-time control happening at the lower distribution end of the grid. In my mind, that's what the smart grid is. It's introducing these new control loops to make the grid more responsive. And as the amount of wind grows, the important thing, the absolutely necessary thing that to enable a large amount of renewables is to enhance the responsiveness of the grid. One other vision for future grid is to introduce a lot more DC, so direct current. At the moment, everything is AC. All our appliances, all of the things that we plug into the outlet are AC. But if you think about it, a lot of them are actually converting that AC into DC anyway. So when I plug in a charger for my laptop or any other computer, there's an AC to DC conversion process that's happening there. Inside televisions, there's an AC to DC conversion process. So there's a lot of different appliances that are actually these days running on DC. So one philosophy is to think about within a home environment or an industrial environment, having DC reticulation out to the various different appliances. And that's what this is showing. It's an AC grid servicing an AC to DC conversion process that is connecting up to some residential down here, some industrial, commercial up there. So it's another vision for how the future of the grid might evolve, and power electronics will play a major role, and that may well lead to this DC sort of sub-distribution and DC form. Okay, so wind generation. There's not a lot of it around here. If you go up to near Lansing, you can start to see some wind turbines. If you head over to beyond Windsor in Ontario, you'll start to see some wind turbines, but they look like that. Is anyone who has not seen grid-scale wind turbine? Okay, so it's a little superfluous. I'm not sure you've kind of, carving their way up in the sky to appreciate the size, but this photograph gives a size comparison of what the blades look like relative to a couple of people standing there. And then I threw in this other slide because it shows offshore construction in the North Sea, where these ships sail out and then lift themselves out of the water and build a turbine, put it all together, drop themselves back into the water and move off to the next turbine. It works because it's relatively shallow. If you're a few kilometres offshore in the Great Lakes, that process is not going to work. And just again, relative sizes. So here's a person standing down here in a car, a house, transmission towers that tend to see around the place, and that's a fairly standard, maybe on the large side, but relatively standard wind turbine these days. And relative to a Boeing 747, these things are comparative size. Okay, so wind, what does the output from wind look like? It shows the total wind power production from across all of California for May last year. And for every day is a different colour, and then the dark red line is the average of all the days throughout that month. So you can see midnight through to midnight, there's stronger winds overnight, greater wind power available. It drops down during the day and it picks up at night. And so that's a kind of an average profile. People sort of are familiar with that general shape for wind output. It's actually exactly wrongly correlated with load, and I'll show some load duration curves later. Most load occurs during this period when wind is at its minimum, and least load occurs during the evening when wind is at its maximum.
So how does the thumb compare with the red line?
Well, this is, so it has the same general
But
shape.
does it come down deeper in the valley?
I'm not even, somewhere we have the wind patterns, but yeah,
There's not enough out there to get in.
it's not enough to really get a good feel at the moment. This shows the total that's average over the entire state. If you look at a single wind farm, it's all over the place. So this is a different day, but it's every day in April 2005 from one particular wind farm. So when you average over a large geographic area, you get a smoothing happening. It's the law of large numbers that's helping out there. When you look at individual wind farms, you don't see that same smoothing. And so here's the average, but the variation is enormous around about that average, and from one day to the next day. So it was just a few days, I guess, it's a bit hard to track, but each day kind of indicates a different pattern. So, the thumb area, being a relatively small geographic area, is going to show a lot of correlation. And when things vary significantly at one wind farm, they will at the others as well. And that makes it much more challenging to be able to track that variation. So that's sort of background to wind. Solar, this is a solar farm in Germany. There's a large amount of solar PV that's being placed across Germany. And then this is just a rooftop that everyone's probably seen somewhere. There's not so much solar rooftop installation around this area because the economics are not there, but there's a lot going in Australia, in fact, way too much for the distribution system to be able to handle. So that's what solar PV looks like. This is what the output looks like. So just a couple of different examples. This is one particular day. When wind varies, it varies relatively slowly because of the inertia involved in the wind. When solar varies, it's clouds coming across. And so a cloud partially obscures a panel, you lose a significant part of the output from that panel. And so you get this very much higher frequency of variation happening in the output from solar. So that's one particular day. This is a different location, just a couple of different days, 28th of September, 29th, 30th September, 1st and 2nd. So 5 consecutive days, but you'll see the pattern of power production is significantly different across each of those days. You can see where it becomes persistently cloudy versus small amounts of cloud with a passing fire. So solar has probably more issues or introduces more issues into the grid response because of this rapid variation. Every time that, in a lot of the solar, especially, so solar rooftop is in residential areas, and residential distribution systems are designed so that the electricity flows from the substation out to the consumer. If you have a large penetration of solar, then you can actually end up with power flowing back from the distribution network to the substation. The voltages move around significantly as that power changes from one direction to the other direction. So when you encounter these types of fluctuations, the voltages are going through some very large fluctuations as well. And people start to get unhappy when their lights go. Mind you, with newer fluorescent lights, you don't see that so much until the voltage either goes so high that they stop working or so low that they stop working. When the voltage goes high, it's degrading the lifespan of all appliances, and consumers don't know that until their bulbs burn out 10,000 hours before they were supposed to be.
Yeah. Now, is that just reflective of the infrastructure itself, the technology used in the infrastructure, the design of the infrastructure?
So it is, distribution networks are designed to be as cheap as possible because they have to span such a large area. And so you can certainly correct for it by putting in more voltage regulation equipment, putting in larger conductors for the distribution lines, but it all costs more. And especially if there's an existing infrastructure, the utility has to come along and rip that out and put up new cabling. So yes, it's an aspect that's associated with the existing infrastructure, but that infrastructure is there, was designed to be as it is for a reason, and it's not well able to cope with these fluctuations. So having said all of that, there's an inverter. So solar produces at DC, and then there's an inverter that's needed to connect it into the grid at AC. So inverters are capable of providing voltage regulation, except that the standards that are written at the moment say thou shalt not do voltage regulation. So there's pressure on the standards bodies to reconsider that and think through what's the right way of introducing this voltage regulation capability at the inverter level. So then every individual house that has a solar panel would be contributing to keeping the voltage constant. And it makes sense conceptually. It's quite challenging to do technically. If you have two adjacent houses that are trying to regulate voltage to different values, you will overload, it will cause problems, hunting type problems between neighbours. And you know how neighbours don't like each other anyway, or when they burn each other's inverters out or something.
So just to clarify, I thought most houses have voltage regulation so that the maximum power set point can't cross certain limits. Are you talking about when the power starts feeding into the grid that you start getting these issues?
No, so it's a passive design at the moment that the utilities say, okay, we're going to have this many houses. That implies an average of each house has a certain amount of load, and then they'll look at what voltage drop that will induce along the line. And based on that, then they will say, okay, this is unacceptable, so they'll do a redesign, or might install some regulator somewhere, but not at the individual houses. So the only thing that's governing, well, for an individual consumer, there are regulations that say your voltage should not vary between lower and upper limit, but there's nothing technically that's preventing it from doing that. So if you went and measured your voltage, which I do at home, engineers are like that, but if you measured your voltage and saw that it was outside limits, you could complain to your utility and they would have to do something about that. now. So there's nothing technically that is holding the voltage at its set point at the moment. It's just sort of a design and leave it and hope for the best. And generally consumers don't check what the voltage is, so the utilities are happy with that.
Do you have an Albuquerque plot?
For solar.
Solar. It's pretty nice.
Okay. These are from Australia.
Okay.
Yeah. So Albuquerque
It's got a nice sine wave.
because it's so high, there's not so many clouds.
There are clouds at times, but there's an individual in Ipsy that has a house in Albuquerque, and he's got his solar generation, well, his whole house load capability being output so he can view it on the internet.
Yeah, okay. That would be
So
interesting.
his has some very nice plots.
Yeah. I'm sure everywhere has non-cloudy days except in Arbor. Okay, so you mentioned the capacity factor earlier, or utilization factor. So this is typical capacity factor. Capacity factor just is a measure, a ratio of the amount of energy that's actually produced divided by the amount that could potentially be produced if the plant was running 100% output for 100% of the time. And so nuclear is, I actually thought it would be higher than that, but it's 92%. So nuclear runs most of the time, 100% output, and there it stays. Coal is about 74%, and then things drop off from there. So combined cycle natural gas, hydro, petroleum, simple cycle natural gas. So the capacity factor for solar is typically less than 25%. So if you have a 10 kilowatt, say a 10 kilowatt panel on the roof, which is kind of big, but it's a nice round number. What that's saying is it's that 25% capacity factor is equivalent to having a constant supply at 2.5 kilowatts. And it's taking into account the fact that during the day you're getting maximum production, but at night you're getting nothing from it. And even during the day you're not getting maximum for all of the day because of the angle of the sun. So wind is usually between 20 and 40%. If it's down at the 20% end, it's uneconomic, but in its own right, it's uneconomic. But tax credits tend to distort those figures. So there's wind that goes in that's completely uneconomic, but they're getting tax credits on most of it.
Why is natural gas so low? Capacity factor?
Because it just doesn't get used very much. Because it's so, well, it used to be so expensive. Natural gas.
So that's just how it's actually dispatched. It actually could be higher.
Yeah. So you could run. There would be combined cycle plants that are running 100% of the time because you're using the steam for some process. But typically that's not how it works. And then for simple cycle natural gas, so it used to be in the economics of natural gas were a little bit different, that they would only be brought into service over the peak time and they'd be shut down for the rest of the time. So they were just a classic peaking plant. That's not how it operates anymore because natural gas is so cheap. Okay, so again, just sort of some background. Power system operations is predicated on the load that keeps changing, and this shows the load for what's called PJM, which is the market that covers the Pennsylvania, New Jersey, Maryland area. This is a summer profile, this is a winter profile. Summer is, during the day, is dominated by air conditioning, and winter doesn't have that same persistence through the day, but you'll see very much a classic winter type peak where people come home, put on lots of heating and cooking and lights and all sorts of other things. The actual peak here is 140 gigawatts for summer versus a peak of about 97 for winter. So it's very much a summer-dominated load, and that summer load is very much air conditioning. You see this little kink, that's people coming home and doing their cooking and televisions on and all that kind of stuff. Overnight, so here's 3, 4 a.m., the load drops way off just when the wind is picking up maximally. And so this is a real issue for power system operations. This is the perfect place where storage would be very valuable, but to store a significant amount of energy, when you're talking gigawatt hours and above, that's a lot of capacity. You can do it with hydro, like the Ludington plant over on the west of Michigan. Then you can get sufficient capacity for it to make sense. But for batteries, that's a lot of chemistry to start storing gigawatt hours.
Is it correct that there can be no more Ludingtons?
It's the environmental groups
They're
really,
fighting.
yeah, they really don't like dams. They like water, but they don't like dams. Anyway, I'm an engineer. I won't go there. So that's the typical load that's sort of driving power system operations. There's a lot of generation that is taken out of service through this period, and then it has to be brought back into service through here, and then it's taken back out of service. So that cycling of plant it's hard on the plant, but it's necessary to track the variation. One of the sort of goals for the future of charging with electric vehicles is to encourage charging to happen here so that you can push that load up. So when you take a daily load cycle and put it into a week, you start to see a pattern that looks like that. And the process of unit commitment is to establish which generators should come into service and when they should come into service. So it's a big optimization that is based on a forecast of what the load is going to be like. And now, these days, it's also based on a forecast of what the weather is going to be like. And so this optimization determines when and which generators, and will do that to ensure that the generation that is in service can service the total demand at all time. So what this plot shows is the aspect that arises due to wind power variability. So you have base load generation, nuclear plants that can't be taken out of service, and coal plants. So they supply the bottom part here all the time. It doesn't matter what else is going on. And then the top of the curve is the load. So the piece between the blue and the top has to come from somewhere. If you look at wind, so this is a fictitious example, but it's illustrative of how things really happen. You get this wind power that is varying depending on weather patterns, and it's often anti-correlated with the actual demand. And so you have periods like here where there's a lot of wind happening overnight, and so the remainder of the generation, everything else, all the other generation is making up a tiny little difference there. But then you'll find other periods where the load is at a maximum and the wind is at a minimum, and there you need backup generation, you need generation to cover that entire amount of capacity. Likewise, there's a large amount over here. So the variability in wind means that operators have to be scheduling plant to be able to change from large amount of traditional generation to a small amount back up to a large amount through daily and weekly cycles. There's a few other control loops. So unit commitment decides which generator should be in service. It's based on a forecast, and forecasts are always in error. So you need some feedback process to keep matching up the actual generation with the actual demand. So automatic generation control provides that feedback process. I won't go into the details except to say the entire grid is divided up into what are called balancing authorities. So it's like take a piece of the grid, put a circle around it, and then monitor all the flows that cross that boundary and compare what's actually crossing that boundary with what the scheduled amount was to cross that boundary.
Sorry, I had a question.
Yeah.
This is more of just a curiosity, but for these large storms that like we've seen on the East Coast in the past couple seasons, where you're getting a whole grid that's getting really impacted with either high usage or using at home, and then the grid going out, how does the dispatching strategy work then?
It's really challenging. Operations are based on periodicity. Everything repeats. And then you get major events like a storm, like September 11, these unpredictable events that cause the load patterns to change considerably. And so that's when the fast-acting plant, like simple cycle gas plant, will be called into service rapidly to make up the difference. But in the case of this Sandy just recently, they had some real operational issues to try, as they were putting the load back together again, to match these big chunks of load that were coming into service with available generation. And with the transmission, that some of it was out of service because it had been broken, other bits were in service, so they had to use what was available to try and re-energize pieces of the network. It's quite a challenge. There's no automated process for doing that. So automatic generation control is matching, it's monitoring the flow across the boundary and matching that, or establishing an error signal between what's actually flowing and what is scheduled to flow. And it's doing the same with the frequency. So it's saying the scheduled frequency is probably 60 hertz. The actual frequency is 59.99 hertz. So that gives an error signal in the frequency. And then it takes this, what's called area control error, and that goes through a PI controller to produce a change in the generation within that area. So it's an up-down pulse that gets sent out to the participating generators. So it's a big feedback control process that is operating across very large interconnected systems. So the whole eastern interconnected power system of the US spans from the Dakotas down to Florida. It's all operating, it is one contiguous power system, and it's divided up into these balancing authorities, and that's how control is achieved. So I mentioned that just to say, okay, in terms of frequency response,
Sorry, on the previous slide, I couldn't really follow what the second bullet point in that third main bullet point was.
Down here?
Yeah, the generator adjustments.
So there's an economic, to simplify things, there's another economic dispatch, it's an optimization that is saying, given the generation that is online at the moment, given the latest measurement of the load, what's the most economic way of rescheduling that? So automatic generation control takes the schedule from the economic dispatch, this optimization, and says, this generator is cheaper than this one, or it should be favored over this one, and distributes any change due to this in a most economic way across all of the available generation. Okay, so the reserves, the first level of control is a local feedback control, which I won't go into any details. The second level of control is this automatic generation control, and they're working all the time to keep frequency, to keep generation and load balanced exactly or close to exactly. if there's a if there's a large event occurs, like a major generator trips out of service, or as happened in Texas a couple of years back, there's a front moves through and you lose a significant amount of wind generation, then you need to take account of that in what's called spinning reserve. And the spinning reserve just says, I've got to have enough capacity available in online generation that's unutilized to make sure I can cover for the largest loss of generation. So when you have more and more wind, you have to make that spinning reserve bigger to be able to cover for sort of, coincident events where you might have a drop in wind at the same time as you lose some other generation. So reserve actually becomes more expensive. So adding wind costs money because you have to carry more reserve to cover for the possibility of that wind going out of service, the wind disappearing. The reserves are typically made up of generation capacity, but can also be contributed to by controllable load and by quick start generators like gas turbines and other units. Speaking of load control, okay, so I won't go into very much detail at all. This is sort of one of my topics at the moment. There's an enormous amount of capability for controlling load that's air conditioning type load or energy storage type load. With an air conditioner, you set the set point to a certain temperature, but it operates on a hysteresis band. So you might set the temperature to 68 degrees. It will actually vary between 67 and 69. You're kind of oblivious to that, but it's doing that kind of tracking all the time. The control strategy is to move that set point by a small amount, and in doing so, you don't actually alter most of the air conditioners. You're just by moving the set point, the air conditioners that we're about to transition from on to off or from off to on are the ones that will be affected. So if you want an increase in load, you can do so by lowering the set point of the air conditioner. What that means is that the air conditioners that we're about to turn off stay on for just a little bit longer, and the air conditioners that we're about to turn on a little bit earlier. And that just those differences, when aggregated across large numbers of air conditioners, give a sizable amount of load control.
Barring some sort of centralized air conditioner control panel, I'm guessing this is influenced mostly by consumer behavior?
Yeah, so at the moment, consumers they set their set point to whatever they like. The control strategy is not to set people's set point, but to introduce a deviation in that set point. So you might set your thermostat for 72, someone else might set it for 68. This process is that the central dispatcher says, hey, I need more load. I'm going to signal out and ask everyone to ask all the air conditioners to reduce their set point by half a degree. So you think your set point is at 72 degrees, it's actually at 71.5. You can't detect any difference, but that little change in load, when multiplied across all of the air conditioners, becomes a significant chunk.
But I mean, how would you implement something like this? I'm guessing it would have to be in a large controlled facility or somewhere where you actually have access to instantaneous set point changes.
So the technology is available at the moment to be able to get on a smartphone and alter the thermostat at your house. So one can link into that same technology and say, okay, you have specified your 72 degrees, but we're actually needing you to reduce that to 71.5 degrees. There's not any contact with the consumer. It's a totally automated process, and that signal can be broadcast across the internet or any other communications medium to the houses. You've got a smart thermostat there which just internally drops that set point by 0.5 degree. From the consumer's point of view, they know nothing about that.
Well, isn't it somewhat the plan to use the so-called smart meters to communicate with appliances in the house and use that communication path to perform this type of function? That was the goal, and then it turns out that the smart meters are so slow that you're 45 minutes too late to respond. So theoretically, and in some installations of smart meters, they do have that appropriate level of responsiveness, but in other cases, they are just not fast enough. The communications latency kills the whole thing. So, theoretically, smart meters should be able to do that, fulfill that role. In practice, utilities have implemented something that's basically useless. Well, are they going to use it for larger, bigger load problems?
Basically, all they can do is read meters, which is sort of a...
Well, what I was thinking of is in terms of, maybe you'll get into this, the problem of wind generation in relationship to the capacity of the instantaneous response or relatively instantaneous response part of the system. And all of a sudden you've got a load. If you designed, well, let me put it this way. We have this goal that was put forth to the voters to achieve 25% renewable by 2025. My calculations indicated this would be probably totally impossible. And so under those conditions, the real problem is wind generation is available in a short period of time that you illustrated, and at a time when you don't need the power. And if you're going to have to supply integrated over the whole year 25% of your energy from renewables, then my calculation was that you would need to have wind generation capacity approximately 1.2 times the present coal generating capacity, and still not eliminate the coal generating capacity capital equipment. So it's just not an economically viable approach. But in that case, if you look at it from the standpoint of summertime air conditioning loads, which are stressing the system in terms of capacity, then by a slower modulation of the load demand, by basically shedding air conditioners, you could reduce the demand on the peak capacity of the system.
Yeah, it gets complicated. We should come back to that because I'm sort of conscious that they're running out of time. Okay. There are different types of controllability. This gives fast controllability, but to actually shift large amounts of load to overnight, air conditioning is not going to cut it for you. But you can utilize thermal storage in large buildings, for example. But we can chat about this after. This just shows, using that control strategy, that this is an output from a wind farm in Minnesota, Buffalo Ridge, and the output from the wind farm is moving around. Using that control strategy, one is able to cause the load of the air conditioners to almost exactly follow that variation in wind. So you can levelize these faster fluctuations. So, we're talking hours along the scale here. There's variation that's happening. This is the error. this is the level of controllability that's required. So the nominal set point is 20 degrees Celsius. The maximum deviation is 0.1 of a degree Celsius to create a significant change in total load from the air conditioner. So it works very well. Modulo, the technology needs to be there to provide this communications path. Probably, I won't go into any details except to say there are voltage, we've talked about the power, active power control, matching generation and load, but there are voltage regulation aspects that need to be carefully thought through as well. You have wind farms that are owned by different entities and developed by different entities using different equipment, and they have to be able to coordinate with each other, and that's a real challenge at the moment. Pretty pictures. It's probably not worth going into the details, except to say there's two different control strategies in action here. There's the variation due to the wind, and it's all very colourful. The other thing that is important, though, is regulating the voltage at the terminals of the wind farm, which are the blue dots, doesn't guarantee that the voltage at other points in the network is regulated, which is the red dots. And there's been this misconception that so long as I regulate the terminal voltage of the wind farm, everything will be all right. What we found in the thumb area is that is completely the wrong thing to do. And the conclusions, just, renewables are going to be increasingly important in electricity generation. There's this mismatch between where you find the renewable resources and where you find the population. And then there's the variability inherent in the renewable generation that causes all sorts of challenges for the grid. Okay, so anyone who wants to leave, feel free. I won't be offended, and anyone who'd like to ask questions, that would be great as well. It might be good to turn the lights on so I can actually sort of see people. I think there was a question up the back.
How easy is it to prepare wind and solar? How fast can it be done? I mean, if you want to do it for economic reasons, to reduce, for example, the variance, is it done easily?
So it can be done quite quickly. In the case of wind, it can be done in a one-way direction. If you want to curtail, it's easy. You can just spill wind by rotating the blades, increasing the pitch angle, and that makes the blades less aerodynamically efficient, so you lose mechanical torque and you lose electrical torque. So you have a one-way, you can drop power fast, but you can't increase power. That's with wind. With solar, there's no moving parts in solar, and so you typically solar is being operated at its maximum power point. There's control algorithms to do that. You can very quickly move it away from that point. Nothing, no mechanical parts, it's all electrical. So almost instantaneously you can drop output from solar as well. But again, you can't increase. It's a one-way control mechanism.
And is it being used currently for reducing the variance or a way to control that?
So solar hasn't, because there's not enough of it to really make any difference. In the case of wind, there is this spilling that goes on. The wind farm owners don't like that at all because they get the tax credits based on the amount that they sell into the grid. And whether it's needed or not, they still want to be dispatched. But there are operational rules that are coming into place. There's rules already on emergency conditions that you can drop wind, but that's a really crude way of opening a circuit breaker, and the whole wind farm goes away. And the owners don't like that either. In a more controlled way, there's not the regulations, the sort of procedures in place at the moment, as far as I know, for deliberately shedding wind in a fast response.
In terms of meeting like larger goals, like the RPS of say 25% of the whole generation, how are countries like Denmark, who are already at I think 20 or 25% wind, and Germany at 20 or 25% solar, how are they meeting their whole country's demands with the variability?
They're leaning on France's nuclear. And when the French nuclear goes away, they're completely stuck. But it's just such a large system that they can lean on the neighbours in a meaningful way. So Denmark boasts of 40% or more. There are times where the wind output exceeds the demand of Denmark. But it's easy because they've got Germany right next to them, and they've got these massive loads all around the place. But the way it's done is it's just relative to the country's demand, it's big. Relative to the whole interconnected European system, it's not that big. It's still bigger than the US, but it's much more manageable.
Well, so then, but if just Michigan were 25% wind, but we're connected to the whole eastern grid, isn't that the same solution?
So the rule that was proposed was that 25% of the energy that was sold in Michigan would come from renewable sources. So that's saying you can't buy from the other states. You have unless you're buying renewables in from the other states, then it doesn't satisfy that 25%. So it's a different way of counting a different way of counting the interconnection. So you could build 25%, but then when it goes away, you would need to have significant interconnection capability with the neighbouring states, and as the existing transmission wouldn't be capable of meeting that increase in flow from the neighbours.
If a region were to have a natural gas baseload, would that be more amenable to having like wind turbines around because they would ramp up, ramp down if there was an influx of wind?
Yeah, except that if it's simple cycle, if it's simple cycle, yeah, it's very responsive. If it's combined cycle, it's just about as unresponsive as base load because you then are trying to match up, or you have to be very careful about matching your electricity production with your steam production, which is presumably going off to some other process. So a combined cycle there are operational difficulties with combined cycle as well. Simple cycle is very easy, but it's not a good use of resources. It's not very efficient, but it is very responsive.
So that's not a scenario people are looking at with retiring coal or replacement natural gas?
It is, but I think it's a short-term solution. It's very difficult to encourage investment into nuclear or coal. When you're thinking sort of base load, typically thinking $1 billion to $2 billion. And it's hard to get people excited about spending $2 billion when they look at the electricity industry and don't see any guaranteed return on their investment. So people are building smaller gas-fired power plants, which do, because of the responsiveness, because of the smaller upfront cost, do make sense from a return basis. The difficulty is that the gas pipelines are not being enhanced. So a few years back, they nearly had a pressure problem in northern Wisconsin because around Chicago they were sucking so much gas out. It was cold winter. They brought in a lot of new gas-fired power plant, and so Chicago, Milwaukee, Madison area was sucking a lot of gas out of the pipeline, and it nearly flamed out up in the north of the state. So there are issues with transport of natural gas. Now I think that's changing because the fracking's happening in all sorts of different places. And so the pathways for gas are not totally dependent on coming out of the Gulf area. There's more diversity. Personally, I think fracking is a little bad. Anyway, just put that out there. Yeah.
Quick question. You mentioned that voltage regulation at wind farms is a bad idea. But you mentioned that voltage regulation at the solar panel with the inverter is a good idea. How do you rectify those differences?
When you're talking a wind farm, it tends to be remote from where the load is. So what happens is that you regulate the voltage at this point where the power is being injected, but you're injecting a variable amount of power. And so you have a variable, the voltage drop across the interconnection changes as the power flow changes. And so at the next load bus along, you're holding the voltage solidly here, but they're seeing this voltage going up and down out there. When you talk about solar, you're sitting right at the load, so you're regulating the voltage at the point of the load as well. And so you don't have the voltage drop across the interconnection, so you don't have that issue. You had a question?
If the economics are there as far as most of the